Hey, thanks. I was going to introduce myself, but thanks for that great introduction. So I guess we can just hop right in. So first, I'd like to give everyone a brief introduction of what capabilities and features Michelangelo's Palette feature store provides. Our feature store serves as the backbone for dealing with data in ML. One of the first steps when you're dealing with data in ML is feature preparation. Palette aids users here by auto-generating batch pipelines and setting up streaming ingestion services. If the necessary features are already available in our common store, Palette can help discover and analyze them. This beats manual selection or brute force iteration over many feature types. And here in the center and at the heart of any feature store is the actual serving of features. Palette provides APIs to consistently serve the same features from both an online database and offline batch systems. Low latency, high availability, and low cost are the name of the game here. Palette also provides automated monitoring systems to notify users as early as possible of any failures or issues with data quality. Bad data is just as detrimental to prediction performance as a bad model. Lastly, depicted here is the Michelangelo transformer, the convenience APIs provided to join and transform features consistently online and offline for a model. So next, I'd like to go over just a brief history of Palette's evolution to help understand how we got to where we are now. Back in 2016, 2017, we launched and made public the industry's first feature store. This had the core components that allowed for storing Uber's ML data in one repository and serving it online and offline. At this time, the focus was on batch features. Next, then, as Uber in its own As its use of ML continued to scale, Palette needed to go through its own growing pains and meet the strong demand. This meant optimizing for latency and high scale of millions of QPS. At the same time, more support for streaming features was built into the platform. After data could be served at scale, a couple of years ago, the focus shifted back to the data itself. Were teams ensuring that they're using the best features and ensuring they remain high quality? We added automatic feature selection and tools to ensure high data quality to address these concerns. And that brings us to today, where we have focused on feature APIs, embeddings, and reliability. Today's talk focuses primarily on the feature APIs and its related metadata, which have helped ensure seamless operation and better modeling of complex systems. So what level of scale are we looking at in Palette? Our online serving systems serve a wide array of use cases across all major Uber products, such as Eats, Rides, Safety, all summing up to over tens of millions of requests per second, and with P99s under the 10 millisecond range. Offline serving is also no small task, with some single training jobs reading up to hundreds of terabytes of data per training run. Along with so many models comes thousands of feature pipelines. With so many touch points, it is key to have a highly available and reliable system with minimal user involvement. Lastly, in the topic of today are metadata changes, which are in the thousands per week. With many moving parts, feature deploys, and code deploys, it is essential to avoid metadata changes negatively affecting production services. As a platform at this scale, any small cracks in the system can have an outsized effect. So what high-level problems can a subpar metadata system cause? First off is unreliability. When bad metadata changes are deployed across the system, it can negatively affect any number of services and products. Second is slow developer velocity. Without clean APIs and tooling, the system can be difficult to operate and debug. And lastly is customer dissatisfaction. So we want to feature store users and our team alike find it a breeze to work with anytime working with data for ML. So now I'll provide a couple of problematic examples to illustrate all these potential gaps. The first is the system misbehavior. So first off, we have an example of the bad config being deployed online. This could be a change such as adding a new feature group incorrectly, or maybe a change which routes requests to an online database cluster which hasn't even been created. If this change gets rolled out, it causes serious effects for downstream services, such as causing bad recommendations in the Uber Eats home feed, or any other product. So if these changes are rolled out quickly and with no auto rollback mechanisms, this could spell disaster. Second, we can have inconsistent metadata in the system. Depicted here on the slide, we have user order features writing to one online database, but the recommender service is trying to read the data from another. Reader and writers of the feature data are not in agreement of where the data is even residing. This can be caused by multiple sources of truth, such as configs living in separate repos. Another cause can be incorrect coordination of metadata rollouts, such as the metadata change being landed, but not yet taking effect in the live system. Without tools to fully understand and strictly control the state of the system, services are unnecessarily exposed to risk. And our last example here is high operational complexity. So in the image here, you'll see a complex web of where services fetch their features. Many use cases across Uber require isolated environments to avoid noisy neighbor effects. We don't want one high spike in QPS from an experiment or relatively unimportant use case, bringing down the most important models. This results in unique setups per isolated environment. Also, many of these cases are such high scale to require multiple database clusters as well as caches. This adds even more complexity to the web. If all these cross dependencies need to be constructed and maintained through manual metadata changes, there are many touch points for failure. So our new API and metadata design are targeted to solve exactly these problems. We've introduced much better validation. We now maintain a strict schema design with added semantic checks to ensure cross-entity consistency. And this helps catch bad configs as early as possible. We have further unified the metadata. Instead of configs living in multiple systems, we've centralized them all under one roof. This simplifies everything and allows for better cross-entity validations. Third, we have made the system easier to operate by being more dynamic and automated. Time to deploy and validate changes has been significantly reduced. And finally, we have added new abstractions to simplify the complex web of configs, providing for better modeling of the problem space. So now I'd like to hand it off to Paarth, who's going to dive a bit deeper into each of these solutions.
Awesome. Thank you, Nicholas, for the wonderful journey so far. So as Nicholas was just starting to talk about the solution aspect of how we solve these problems, these are some of the principles that we wanted to keep in mind as we were building the solution out. So first is we wanted to have like APIs for all our first-class entities that we define in the system and we want to clearly identify. And then we wanted a solution which could work well if we build a UI on top of like our whole metadata system, as well as we support like code-driven interactions for interacting with the metadata. Thirdly, we wanted consistency, making sure like all the metadata pieces live together. We have a clear way where metadata entities can interact with each other. And there's no fragmentation at all in how metadata is structured and where it's placed. And then lastly, we wanted to make sure our solution is such that we can extend it for very future use cases that we haven't even anticipated completely yet. Yeah. So next slide, please. So looking at our Uber experience of how, we built the Palette feature store, and Palette being the first feature store, we have like, tried to scale Palette to millions of QPS. And with that experience that we have across like managing this complex millions of QPS across Uber, we took those insights and we came up with this unique, schema and you can say object model here. Specifically, features is obviously the heart of the ML system here, and feature group. When we say here feature group, it means it's collection. It basically can have collection of features which are correlated under the umbrella of a feature group, right? Now, we introduced a concept which is pretty unique and not heard of anywhere else. It's called online feature serving group. Now, this concept comes from our years of experience of how we manage the infrastructure underneath to support this much scale. So online feature serving group, what we mean here is a collection of all the various storage entities that basically come together when we need to serve a particular inference server, for example. And we'll go into examples of how we have structured this for various use cases. But it's an abstraction that helps us cleanly bring all the storage entities together. And then from an inference server perspective, we don't need to leak any of the storage details to what in the inference server level. The inference server just knows that, yes, I need to talk to this entity called online feature serving group. And the rest of the details of what storage exactly we need to fetch features from, where do we need to cache these features, all of that is abstracted away. So it's a very clean abstraction. Similarly, is the case for a feature group, where feature group, let's say, is dispersed to various online storage systems for online serving. But we don't want to leak these details completely in a place where the inference server now needs to care about this. So feature group also has a wonderful abstraction and link with the online feature serving group. And that way we bring all of these hardware, storage abstractions very, very underneath in one umbrella. And all of the other entities don't need to care about it anymore, which makes it very easy for us to navigate the system. And for customers, for the Pallet basically on calls, and Michelangelo engineers in general to interact with the Pallet ecosystem. Yeah. All right, so we can go to next slide. Yeah. So here is an example, basically, of one of the tenets that we were talking about, right? And Nicholas started going into that, which was cross-entity validation. So imagine we have a bad configuration, and as Nicholas was mentioning, when the bad configuration lands into a production system, it leads to actually, surfacing either error messages to the user or a poor experience where the recommendations are of not good quality because we had a bad configuration, which leads to bad predictions. So to prevent that whole chain of bad predictions, what we have done is we introduced this feature validation service, which can basically, given a metadata configuration, it can validate across all the entities that we've mentioned in the previous diagram, and it can validate and make sure the whole health of that entity ecosystem is maintained before the configuration is deployed to production. In that way, we catch any metadata problems right at the code review time itself. We don't let it go beyond code reviews. So that's something we introduced here to make sure like no bad configurations can be deployed ever to production from now on. Yes. Yeah. Yes. Next slide, please. The other problem that we had was like our configuration was fragmented in many different systems. To give an example, we had like a cache configuration, which was living in one particular metadata system. There was database related configurations of which feature groups connect with which databases, and all of that abstraction, all of those storage level details that was living in another ecosystem. And then we had streaming features related configuration, which was living in third system. And then we have the metadata repository, which is like the central place where our customers interact with Pallet. That was living in another system. And basically, we were in such a mess where all of our configurations were in these different systems. And imagine a new engineer coming to our team, and then like the complexity in which they are interacting right now, and like the confusion in which like they have to navigate to make sense of the metadata, is very complex. So we took that feedback from our new engineers on the team. We took feedback from our customers, and we started rethinking. We were like, this is not the way we want to design a new system. So we wanted to unify all of these different metadata systems in one place. So what we did here was we eliminated all of these different various metadata systems, and instead unified all of that in our metadata repository, backed by a schema that we talked about in the previous diagram, the object model, right? That way, all of our metadata now is in only one place. Customers and Pallet on calls, everybody has only one place to go, one single structure to interact with. There is a solid schema now. and there is only one system which pushes this whole metadata to the online serving as well as offline serving. So which makes life very, very simple for our customers when they want to track a metadata change, and also for our on-calls when they want to interact with the metadata and want to track and see where the metadata changes are for a given particular change. So we unified everything under one umbrella now. We eliminated everything, all the other configurations, and now life is very simple to interact with as everything lives in one ecosystem now. Yeah. All right, next slide. Yeah. The other major change we did was previously our metadata, the way we were interacting with it and way we were actually trying to push some of the changes to our offline and online serving systems. Anytime a user or a Palette on-call makes a metadata change, we would iterate through literally, and you can imagine in the previous slides, Nicholas was mentioning there are thousands of these metadata changes happening on a regular cadence. And imagine having to iterate through all of them every time, even one change is happening, we're iterating through all of them, which is there in the metadata repository, and then trying to push each one of them again back to offline and online serving. And imagine as the metadata, as the number of feature groups grow, the scale at which the push is happening is super slow. And when you make one small mistake in the system, the rollback is also extremely slow now, which makes the whole system extremely slow to interact with, very fragile, and leads to a lot of online serving issues, offline serving issues. And the speed at which we can react to a problem is very, very slow. So which means we hurt the business a lot in this case. So we wanted to redo this whole push system because we felt we had opportunities to enhance the system. So instead of making it a full push system where we go through all changes or all particular metadata at once for any small change, we came up with this incremental update system where whenever a metadata is changed, we look at what particular metadata has changed. We only pick those changes and push them to offline and online serving systems in an incremental manner. That way, the speed at which the push is happening is coming from hours to minutes. And also, we are able to react much faster when there is a problem. We're able to link all the alerting with this incremental changes, and we are able to roll back automatically when there is a problem now. So, and the rollback speed is also super fast because we are only pushing what we have changed. So the rollback also means we can react much faster now. Yeah. All right, next slide. Yeah, so the other part to our pain of the old metadata system was because we had this many configurations living in many different places. That was one part of the problem. And another part of the problem was our online serving system. It was basically linking with the whole metadata as a code. And, generally there's a principle about making sure that your config lives in a different place, your code lives in a different place. In our case, we were mixing up the code and the config, right? Excuse me. So because the code in the config was mixed up completely, every time we had to make a config change, we had to deploy the config as part of the online serving code. And the rigor obviously is much high when you have to deploy a code change, which meant that we always lost 1 to 2 weeks for any small change. And this is frustrating for our on-calls, frustrating for our users, having to wait for any small change to be deployed. You're waiting now 2 weeks and you lose such velocity, which means that you could iterate on things much faster, but now you're losing time just for the deployment's sake. So we as we were unifying the whole configuration system, we also wanted to make sure we stick to the principle where no config lives with the code anymore, and we eliminate all the configurations that are living in the same place as where our code lives. So we redid, as we were revamping this, we brought all the configurations inside the metadata repository, and now you can see the number of steps is also reduced, and also we no longer need the deployment to happen with the code now, which means configuration changes, they get deployed in order of minutes, and we have eliminated the whole cycle time for waiting weeks to interact and really use Palette. Yeah. So that's how we've automated the whole the onboarding system to Palette, and we also reduced the number of places where configuration is living going forward. Yeah. Right, next. Yeah. So coming back to online feature serving group, I want to go slightly more deeper into that concept because it's a unique thing that we have introduced here. And this diagram depicts the problem that we had before, where we have a recommender service, we have a pricing service. All of these services need to know which particular databases they need to interact with to get the features, right? And on the right side, we have these various feature groups, like restaurant ratings, user orders, demand and supply. And all of them also need to interact and say, yes, these feature groups need to be dispersed to database 2, database 3, database 1, database 4, right? And you can just imagine the complexity when you are interacting with, let's say, hundreds of features, and just visualize the messy graph you would land into, right? Where and this was exactly where we were. Anytime we had to even change, let's say we had to make a hardware upgrade. Now we want to move from database 2 to database 5. Now we need to know, we have to build this graph ourselves to even visualize, okay, which particular feature group, which particular service is interacting with which database, and which databases we need to update to even migrate, right? So that was the complexity we were dealing with. And any database change, we would be, any database upgrade, we would be looking at months generally to make sure we don't cause any outage anywhere. So that's the mess we were in before. Now with online feature serving group in the next slide. Yeah. So with the abstraction that we have created, it's such simplified system where all the recommender service, pricing service, all the feature groups, they only need to care about which online feature serving group they talk to, right? And which they link to. And that's the bridge between your online services or your feature groups. And that's the abstraction we created. Underneath, if you want to swap out a database, let's say 2 with database 5, there's only one place we need to update now, pretty much. And other places don't need to worry about those aspects, which means it's a clean abstraction, and only one place that the on-call needs to care about. And that way, the whole migration of particular database is so simple now, and also easy to visualize. As you can see, the graph is very simple to visualize here. Yeah. So the online feature serving group has simplified our interaction with the storage entities, and we have simplified our on-call lives thanks to that. Yeah. Yeah. Next slide, please. Yeah. So with migrating to the new system, we did encounter a lot of challenges. Now, as we know, Palette is at scale, running at millions of QPS. Any small metadata mistake is a recipe for an outage, right? So we had to make sure first we do our due diligence, comparing the metadata between old and new systems so that we have parity in the metadata, right? And then for which we used a thorough metrics between old and new metadata system. And we also made sure that the data integrity is preserved between the old and new system. That way, there is no mistake whatsoever as we are migrating, right, with this. For our offline ecosystems also, we did something similar where we did thorough testing, we did thorough metadata comparisons to make sure everything lines up as we are moving the offline ecosystem, which where our training and other ecosystems use this metadata to make sure the training happens in the right way, right? We had a solid rollback plan where we had a kill switch, which could flip which system we read the metadata from in matter of like minutes, basically. So any mistake we would want to make sure like we could come back to the old healthy system and quickly, right? To make sure our customer lives were easy as we were migrating, because we changed the underlying structure of the new metadata. It was backed by a new schema. The old metadata did not have any schema. We did automated backfills from old to new metadata. And then our customers, when we were onboarding them to the new system, we had clear onboarding docs. And we made sure that because we had the automated backfills, customers didn't have to worry about creating those new metadata files and new metadata entities. We did everything for them, and they just had to use the new onboarding docs, and that was it to interact with the new metadata system. I'll hand it over to Nicholas to conclude here.
Yeah, thanks, Paarth. So to wrap things up, we'd like to reiterate some of the benefits we've seen from improving our APIs and metadata ecosystem. First off is ease of use. So with these new abstractions and more automation, we are no longer hitting a lot of the misconfigurations that used to occur. What might have been multiple code changes before is just a single one. Second is reduced maintenance and operation cost. We've reduced the number of moving parts in the system, making for easier updates. This improves the process for adding new capabilities into our system, as well as performing tasks such as migrating from one online database to another. Next, we have reduced deployment time and customer onboarding times. By clearly separating out code from config changes, now we can have a simpler rollout flow that is independent of the code changes in CI/CD. So changing the metadata backbone of a system such as Feature Store, which has so many moving parts, was no easy task. And we are happy to now be seeing these benefits of our hard work at the end of this year. So shout out to all the members on the team listed here on the slide who also helped make this happen. And we'll soon be publishing a blog with more details on our journey and hope for all of you to tune in. So I think we might have a couple minutes for questions now. Thanks, everyone.
Brilliant. Thanks, Nicholas. Thanks, Paarth.